All right, let me get a big screen here. So this is something I've done before. I'm going to go from algebra to geometry to precalculus to calculus, and I hope I can do so in like 15, 20 minutes. The reason I'm doing it again is I think that repetition is very important in trying to explain things as well as how to learn things. And so by doing this again, I'm hoping I can streamline it a little bit and maybe have a little bit more succinct presentation. All right, so let's start with algebra 1. Then we'll go to geometry. And by geometry, I mean shapes, not congruency, not proofs, no. Pre-cal, talking about what I think are the most important things to improve one's ability to think mathematically. Talk about some of those fundamental thought processes, I hope. And then I'll put the cubic in graphing form without calculus, based on the geometry of a cube. And then I'll do the same thing with calculus to show you that the graphing form for a cubic was there all along, but folks probably didn't polish it off. I know I didn't for many years. So that's where we're going with this. And we'll start with algebra 1, which means that you get familiar with a number line. And what you do on a number line is you look at numbers. And if you want to do a calculation, you got to start with a number and put it into a calculation in order to calculate and get an answer. So the x-axis I'm going to start calling, pick a number and calculate with it. I forgot to write with it. Okay, pick a number. And if you want to get good at calculations, you got to calculate, which is why I think sometimes transformation gets in the way of that, because people don't have a good feel for the cubic, and yet they get quickly said, well, how do you shift and where? Okay, I don't go that route. So y equals x cubed is a calculation. And if we pick a number, 2, we do 2 times 2 times 2. Look at I picked something and I did the calculation and I get 8. Well, if I put a dot at 8, you'll never know what number I started with. So what we do is we go up 8 units. 1, 2, 3, 4, 5, 6, 7, whatever. And we say I started with 2 and I got 8 as an answer. And that's what it means to plot. And we have this thing called the y-axis, where that's a height of 8. And the y-axis then becomes our answer axis. But you can move that, slide it, that y-axis, and measure 8 that way. I can kind of see that that's my answer is 8 when I pick 2. Kind of what we do. So I looked at the cubic and I picked some numbers. Come on, Rene Descartes. I picked a bunch of numbers and I looked at -3 times -3 times -3. So that's a perfect cube. -3 times -3 times -3 gets us -27. And I don't know, that's hard to talk about volume out of the negative. But -2 times -2 times -2 is -8. And we can see that we went up from A to B at about a 19 to 1 clip. And from -8 to 1 is a 7 to 1 clip. -1 to 0 is a 1 to 1, 0 to 1, 1 to 1, 1 to 8, 7, 8 to 27, 19 to 1. And you can kind of get a feeling for the shape of the graph by just looking at those rates of change. We call those average rates of change. All right, and that's embedded in our cubic. And it seems like our cubic is changing least quickly at 0. And I want to look at geometrically why. But if I want to talk about how things change in an instant, then I don't want a big jump from -3 to 2. No, it's easier to look at the positive numbers. I don't want to go from 2 to 3. I want to go from 2 to 2.001. And that gives me a little snippet. And when you zoom in on a little snippet, it looks linear, which means you can talk about y2 minus y1 over x2 minus x1, which you learn in algebra 1 is how we find the change of a line. Well, if we can zoom in on a curve, we can talk about linear change for curvatures. Because when you zoom in, it looks like a line. Okay. So here are some values. right? And if I look at the first three decimal places, there's no change at 0. Whereas at 1, you're actually going up at 3 to 1 at 1. But from 0 to 1, you're going up at 1 to 1. And from 1 to 2, you're going up at 12 to 1. I'm sorry, 1 to 2 is, what did I call it? E to F. And from E to F, you're going up at 7 to 1, right? But those are big jumps. These are little jumps. And you can pause the video. There's actually a formula for how these numbers are changing. 12 at 2, 3 at 1, 0 at 0, 27 at 3, right? And that gives you a sense of at 0, 0 for slope. At 1, 3 to 1. At 2, 12 to 1. At 3, 27 to 1. And I hope you can start to get a feel for those changes at those instances. All right. Now, the more I change from 4 to 4.000, I could put more zeros in. So maybe if you looked at those table values, you could tell me what I get right now. If I cube that, I'm not doing this with a calculator. No. So pause the video and see if you get this answer. There's 7 decimal places. So I'm going to do 7 decimal places, and I got to do what's called the derivative in my head right now. Yeah, I think I got my change. See if you get this change. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I believe that's what you should get. Now, it's going to be hard to find a calculator that gets you that many decimal places. But it comes from the geometry of completing the cube. And I'll get to that later in the video. And now we could actually write the equation of the tangent line. Because I think I'm dividing 0, 0, 0, 0, 0, 4, 8 by point. That's a point right there, right? 0, 2, 3, 4, 5, 6, 7. I think it's 48 to 1. So therefore, the equation of the tangent, which I can't really draw because it really would be superimposed there, would be a slope of 48, x minus 4 plus 64. So we know the original function is 64. Y equals x cubed is 64 at x equals 4. The y, the answer is 64. So we got location and we got rate of change at that location, all embedded. All that information comes from one line of work, which we call the tangent line. And I'll find that formula for you later in the video. Now here's some cubes where you can kind of see changes, right? There's a lot more change in volume from here to here. A lot more change. It's not constant change, right? More change here. Where are things changing least quickly? Well, I hope you say right here, right? So maybe that gives you a little feel for the point of inflection, right? My slopes, my average slopes went from 19 to 7 to 1 to 0 to 1 to 7 to 19. Well, I can see my slopes are doing what? Decreasing and then increasing. Well, we say that's a change in concavity. Now, slopes, you can think of slope as velocity. So what's going to make your velocities change like that? Well, if you're in a car, brake. What's going to make your velocities change like that? An accelerator, a gas pedal. All right? So we can begin to start thinking about that as just initial amounts, y prime, how they're changing, and y double prime talks about acceleration, how the velocity is changing. Right? And that gives us a segue into physics. Now, I should have called this Algebra 1 to geometry to precalculus to physics to calculus. I don't. But this is what I'm referring to as a perfect cube. And in this case, it's a 3 by 3 by 3. And if I went to 3.01 I get 27.270901 is what I should get. As long as I'm not half asleep late in the day here and making mistakes. I don't think I am. So that would be a 3 by 3 by 3. And now it's time to bring out a manipulative just to show you what's happening here. Well, here's my 3 by 3 by 3. And what I'm doing is I'm putting a sleeve of change. Let's get that sleeve of change right here. Okay, there it is. My trusty box of refill markers. And I'm going to put that right there in the front. I'm going to put down the top and the side. And I have just added a layer of volume to this box. At what rate am I adding the layer of volume? Well, when the box is this size, my rate of change is this size. If the volume was a die, you know, like Monopoly, playing the game real little, well, I don't think you'd get as much change when you slap layers on it. And this layer is actually being represented by that amount that I've added to the 3 by 3 by 3. So where is that change coming from? Well, what are you looking at for a shape? What are you looking at for a shape? What are you looking at for a shape? I see a square. I see 3 of them. And what's 3 times 3? 9 units of area for that. 3 times 3, 9 units of area for that. 3 times 3, 9 units of area for that. And 9 plus 9 plus 9. No accident. And the volume, the last dimension, is actually the thickness of the layer. Can you see it? What am I using to represent that thickness? 0.01. So we're coming back to this a little later in the video when we start doing some manipulations with calculus. But right now, I don't think I'm doing anything other than playing with a box. I could have done that in 2nd grade. 3 by 3 by 3, elementary school. Cubing that, yeah, it's tedious, but it's still just straight calculation. Y2 minus Y1, X2 minus X1 gives you a feel for rate of change at that instant. All right, so let's actually get a cubic here. All right, there's the one we're familiar with. But I know cubics come in a lot of different shapes and sizes. So what if this was the cubic that was under consideration and I wanted my point of inflection to be at 4? Well, we already cubed that. We know that's 64. And now what's the rate of change there? Well, maybe you can get it. Did we do it before over there? Yeah, we did. It's 48 to 1. So this is 48 to 1, and looks like I'm going down at that instant. Okay, but hang on here. I got to go back because I actually put something in graphing form, and I don't want to start the video again. So I lost my train of thought. I actually took x cubed. This is the graphing form. All right. I changed it to this equation here so that 4 gets me minus 73. All right, so I know the location. Okay, and I hope I really did this calculation quickly. If I have to do the video again, I will. I hope all of these numbers work out. It's the end of the day, and I know me now. Ooh, end of the day, we're taking our chances. All right, so I can see that there's change at the point of inflection that I don't see in the parent function. Well, it actually comes from a linear component. So I decided to write the equation of a line, and the equation of a line tangent to this is, I'll put it here, minus 50, x minus 4, minus 73. And we've practiced writing the equation a lot, equation of a line a lot. So that should make sense. Little snippet. Okay, well, it turns out I got a lot more information coming here that we've been talking about. The rate of change at the y-axis. Well, I have to actually multiply that out. And I've multiplied that out. And we can see that equation is 2x cubed minus 24x squared plus 46x minus 1. So I know I'm going up at 46 to 1, probably around here. I'm going up at 46 to 1, and 46x minus 1 is that tangent. And guess what? It's given to me. It's a gift. And we've looked at a lot of different videos in the lesson sets as to why. Not going to do that one again, but I would put what? 0 in, and then I'd put 0.001 in, and I would see that this is the dominant change column. What happens when you multiply 0.001 here? You do it 3 times, it's getting smaller and smaller and smaller. You do it twice, it's getting smaller, not as small as this one, but if you only do it once, this is a lot bigger at 0.001 than this is at 0.001. Right? So that's the dominant rate of change, because that number is not changing. And if you see it change, please write to me and make a telephone call. I'll get back to you. Constants don't change. All right, so I just decided to make this minus 50 just out of the blue. And then I decided to multiply it because this is how cubics are presented in the textbook. And you usually factor and find the zeros. And I think there's a whole lot more excitement going on with this conversation, which will continue. All right, let me get Renee over here in a good spot. Come on, Renee, behave. Renee's making me, I'm having a hard time turning Renee around. I'm getting stubborn. Let me get this chair out of here. God, I'm fighting Renee. Renee, come on. Come on, Renee. There we go. All right, so if I was presented with this, I think it's a 1-minute calculation for me because I've done it a lot. You might take 5 minutes the first couple of times and then down to 3 and then down to 2. You can get to 1 as well. Okay. It would take me 1 minute to get you the point of inflection, the rate of change at the point of inflection, the tangent at the y-intercept, and the x value, which I now know is measured 4 minus, so on this side of 4, my rate of change is minus 50, so I want positive 50, and I am going to divide by 3a, and do I have the a? Yes, it's 2, so that's 6. That's the x value of the local max, and the local min is 4 plus the square root of 50 over 6. And where am I getting it? Well, I guess I didn't put that down yet. Well, what's the rate of change of the cubic? That's going to be in graphing form in a minute. It's 0 here, right? But if we're changing at 51, then it's the interplay of these two. And so when am I going to get that turn? When am I going to get that local max turn? Well, this is always going down at 50, right? And what's the slope? The slope there is 0. Well, I have to counter it by adding 50 units for a rate of change. And that happens somewhere on the cubic. I think it happens here. Yeah. Think at that instant. Yeah. Yeah, we got that cubic, right? And somewhere over here, I'm going up. If I drew it well. Yep, I didn't say anything inappropriate there. Or not true. All right, so how do I find the 4? Minus b over 3a? Let me explain that briefly. All right, so in Algebra 1, you complete the square, which takes a rectangle that is not a square, reshaped into a square, and then adjusted. That's what you're doing. Okay? What I'm doing is I'm taking a cube, right, where the roots we can see are going to be 0, 2, and 10, which I drew somewhere. I did a 0, 2, and 10, didn't I? Yeah, back here. 0, 2, and 10. If I said, where's the point of inflection? I hope you'd put a dot there. And I hope if you looked up, that maybe 4 makes sense in terms of where that's positioned. And what it comes from is adding up 0 and 2 and 10 and dividing by 3. And that's going to be just like completing the square, but it's going to even off the sides of this rectangle into a perfect rectangle. It's perfect cube, excuse me. This cube into a perfect size cube. And then if I get the first 2 terms, which I would for 2x cubed minus 24 x squared. That's going to come out of this if I double this. Well, I'm losing my train of thought right now, but this is just completing the cube. All right, no calculus yet. Still working with geometry. And if you multiply out the cubic, I did over there, right, to get this. Let's go back there, Renee. I did x minus 4 cubed. I did it first as x minus 4 squared because I know the binomial squaring. I multiplied that by x minus 4. I made some columns. I added up the columns. And, if I did the perfect cube, then there would be some trailing linear terms and constants over here. And what I do is I factor a little factoring, and I know I want a certain x value. And so I just make some adjustments, and it was a lot of algebra, but I did it 30, 40 years ago, and I lost all of that on a computer, and I'm not going to do it out now because I'm an old man and I don't want to. Okay, so back to putting it in graphing form. So c minus 3ah squared is going to get me the rate of change at the point of inflection. And this is what I needed to get rid of those loose terms after I completed the cube. These were because I need to get cx, right? So I put what I need there and I take away what I didn't want on all of that stuff, algebraic stuff. All right, and that helped me see the rate of change at the point of inflection. Okay, and I knew the rates had to be offsetting each other in order to get a slope of 0 there. So I played around for a while and I came up with that, and it made sense to work with that and play with the numbers. And so what I got was the opposite of that. I knew that had to be. And so this was the number that I had to play around to get. And it was 2a in the quadratic. So it didn't take me too long to try 3a intuitively. All of this before I started cracking the calculus textbooks. All right. So now we've got ourselves a layer of change, and it turns out that layer of change, after studying calculus, I learned that that layer of change where we put this is a derivative. This is a derivative. And now what would happen if I had a 2 by 2 by 2, I put a layer of change on, and then I put another layer of change on, and I don't have any more layers of change but if I kept putting layers and layers and layers of change on, all those little changes add up to a big change. And what have I got here? I've got 3x squared, 3 squares with a little bit of thickness. So I can go to a graph now. I can graph 3x squared. I can use that parabola to represent all of the surface area change on the cubic, because that's what this is, surface area change with a little bit of what? Thickness, which means area turns into volume. And in calculus, if we kept doing those changes and changes and changes, eventually we'd end up with a 3 by 3. We'd start at a 2 by 2 and we'd be at a 3 by 3 by 3 cube. And these would represent all those layers of change, which almost looks like a trapezoid. So let's do a trapezoid. A trapezoid is a left-hand rectangle. And if I start at 2 cubed, let's see, 3x cubed, excuse me, 2 squared is 4 times 3, that's 12. Times 1 is 12 units of area. And if I use the right-hand side, I get 3 times 3 times 3 is 27. I get 27 units over there with the right-hand rectangle. And a trapezoid is the area of these. And my width was 1. So I cut that in half. And that turns out to be 19.5. But there'd be some error here. There'd be a little error because I've got concave up. I'm connecting the dots. So there's my error. So my actual error area is a little less. And if I look at 2 cubed is 8 and 3 cubed is 27, sure looks like I got 19 units of change. Whereas the trapezoid was 19.5, but it was an over approximation. And what you do in calculus is you use this symbol, the integral sign, to represent the additions of a lot of layers of change. And the area under that curve represents all those layers from 2 to 3. And where did those rates of change come from? You learn how to change these into the parent function, and you put input there, 27, input there. And if you want to see the difference from this amount to this amount, that's called displacement. That's my bad joke, which I've said too many times. And I'm just giving you a feel for what you're going to be doing in a calculus class. And why am I doing it? Because I think you need to think about these things before you get there. All right, this stuff takes time to process. And the sooner you start a conversation and the more times you do it, the more opportunities the brain has to figure out what's going on. And a lot of times to figure out what's going on, you have to slow down what you're doing, or you have to say it fast a lot of times. I tend to say it fast a lot of times because when I teach in a classroom, a lot of times somebody's not listening. But if I say it a lot of times, I generally catch people at some point. And then if students learn how to do it, they teach each other. Okay, so let's go do this whole problem now with calculus. All right, so if I missed anything over here, I don't think so, but we can find the max and mins and all that stuff. And let's hope it matches up. I did a little work over here. I haven't done it all, but we start with the original equation and we take the derivative. So we found out the derivative of x cubed is 3x squared, doubled is 6x squared. The derivative of the quadratic is really about squaring. And if I put a layer of square on there, that's a layer of area added to this. It's got length and width. There's the width, which is your 0.001 here and here. All right. And we've got a couple of x values. The smaller the square, the less the derivative is. The smaller the derivative amount. That was awkward. All right. So 2x times minus 24 is minus 48x. That's a constant rate of change of 46. And if I take that change, I'm looking at 2 times 6 is 12x minus 48. And when does that equal 0? When x is 4. Well, that tells me I get a change in concavity right there. I don't expect you to process all these things, but just putting the thoughts in your head. So the next time you hear it, your brain's already processed a little, and maybe it's got to go bzz, 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 to put the lights on. There's the sun. Well, maybe we move a little bit here in this conversation, and then the next time you move a little bit further, and maybe, not too long, you're going, oh, I get that now. But you got to have repetitive conversations, and you got to get repetitive practice, and we do that in the lesson sets with all kinds of topics. And so what do? I put 4 in here. If I put 4 in there, 64 times 2 is 128. My next number should be, did I get that right? 64, yeah, 128, 3 times this. 360, 384, I think. And this one is going to be negative. And if we put those two things together, we get, where the heck am I? Which one? Oh, I did y prime. Oh, I'm trying to find the y value of the point of inflection, which over there was minus 70. Oh, God, minus 61. Is that what I got? Minus 61? I think so. All right, is this going to be minus 61? God, I don't. 46, I didn't do this out yet. So 4 times 46 is 190 and 36 is 216, I think. I think that's 216 minus 1. All right, I don't want to add that up. I hope it's minus 61. Well, I better do it out. Right? 128. So it's 14, 2, 4, 344. So that's 344 minus, so that's minus 41. Is that what I wanted? I wanted minus 61. I feel like I'm off by 20. All right. Anyway, I got caught up in minutia. All right. If I put 4 in here, I should get a minimum because the slope is going down most quickly right there. So let's put 4 in. 4, 16 times 6, 96. 160 and 36 minus 190, minus double that. So that should be minus 198, 192. 192 is what I should get if I put 4 in there, plus 46. Oh, I already did this, for God's sakes. It's over here and it's minus 50. So that corroborates that. All right, so you could put 4 into what is a formula for rate of change, and that's what you'll look at, calculus. And if we put 4 in here, I'm hoping we get a cut to the chase here because I'm losing board space, right? The tangent there is minus 50 times x minus 4 minus 61. I could have a little bit of math error here, but now how do I put it in graphing form? I'm done. All I got to do is write x minus 4 cubed with a 2 in front of it. So the graphing form was always there. Now, if this is a negative number and that's positive, then you're gonna get maxes and mins. If this was a positive, then things would always just be going up. But at the point of inflection, which is about here, you're going up at a minimum rate. That's a minimum rate. It's got more magnitude than 0, right? But that's a smaller number than 0. That's where you're going down fastest, right there. Okay, and when you put the cubic in, the cubic is always increasing. The rates are 0 at this point, right? It's 0, but otherwise they're always increasing. And at some point, those increasing rates take over the linear function. There, the linear function. All right, so now I'm blabbing. So I'm hoping that some of those conversations have some meaning and for you, and if not, that's okay. They're in your noggin, and if you keep going up the ladder in math, you might remember the geometry of what I've shown you so that what you're looking at might make a little more sense. Okay, hope that helps someone. And if I made a math error at the end, I'm sorry, but it is sound. It is sound procedure. So go to the playlist. You can get more information on completing the cube, on putting cubics in graphing form. I did a 30-minute or 40-minute just putting it in graphing form. So you can get good at this, and then you can put cubics in graphing form in a minute or less. All right, ciao.